Imagine a single explosion so powerful it outshines entire galaxies, an eruption of energy so immense that for a brief moment it becomes the brightest object in the observable universe. That's the raw, terrifying beauty of a supernova, one of the cosmos' most cataclysmic events. But here's the thing, our universe is far from peaceful. It's a battleground of extreme forces where black holes tear stars apart, galaxies collide in slow-motion chaos, and invisible ripples in space-time shake the very fabric of reality. These aren't just distant curiosities, they're the violent, awe-inspiring engines that shape everything we know. Today, we're diving deep into the heart of cosmic destruction, uncovering 30 mind-blowing facts about the universe's most violent events. From the unfathomable energies released during neutron star mergers to the mysterious forces that send entire galaxies careening into one another, this journey will redefine how you see the cosmos. You'll witness the aftermath of stellar explosions so vast they leave behind glowing nebulae like cosmic gravestones. You'll learn how a single gamma-ray burst could strip away a planet's atmosphere from thousands of light-years away. And you'll discover the eerie, almost poetic balance between creation and destruction, how these terrifying events are also responsible for forging the very elements that make life possible. This isn't just a tour of cosmic violence, it's a revelation of how the universe operates at its most extreme. Every galaxy, every star, even the atoms in your body carry echoes of these colossal events. So buckle up, because we're about to explore the darkest, most energetic corners of space, where the laws of physics are pushed to their limits, and the universe reveals its most violent, breathtaking secrets. Let's start with one of the most terrifying displays of cosmic violence, hypernovas. Picture a supernova, but crank its energy up by a factor of 100. That's what happens when a hypernova erupts. These aren't just stellar explosions, they're apocalyptic events, unleashing jets of gamma rays so intense they could wipe out life on planets thousands of light-years away. The sheer scale is hard to grasp. A single hypernova can release more energy in seconds than our Sun will produce in its entire 10 billion-year lifetime. What makes hypernovas so uniquely destructive? It all comes down to their origin. Unlike typical supernovas, which occur when massive stars collapse, hypernovas are born from the rarest, most extreme stellar deaths. Supergiant stars with rapid rotation and incredibly strong magnetic fields. As these stars collapse, their cores don't just form neutron stars, they implode straight into black holes, and in that final, catastrophic moment, the star doesn't just explode outward, it funnels unimaginable energy into twin beams of gamma radiation, shooting from its poles at nearly the speed of light. The consequences devastating. If a hypernova happened anywhere near our galaxy, those gamma-ray jets would act like cosmic blowtorches, stripping away planetary atmospheres and irradiating anything in their path. In fact, some scientists believe a hypernova may have triggered one of Earth's mass extinctions millions of years ago. Yet, for all their destructive power, hypernovas also play a crucial role in the universe. The extreme forces at work forge heavy elements like gold and platinum, scattering them across space, meaning the very metals in your jewelry might owe their existence to one of these cataclysmic events. So while hypernovas are rare, their impact echoes across time and space. They're reminders of the universe's dual nature, both a forge of creation and a harbinger of annihilation. Now imagine an object so luminous it outshines 1,000 galaxies combined. A quasar, the brightest and most violent phenomenon in the known universe. These cosmic monsters lie at the hearts of distant galaxies where supermassive black holes, billions of times heavier than our Sun, devour everything in their path. But quasars don't just swallow matter, they transform it into beams of pure destruction. When gas, dust, and even entire stars spiral into a quasar's black hole, they don't vanish quietly. The material forms a swirling disk of superheated plasma, brighter than anything else in space. And here's where things get terrifying. Some of that material doesn't fall in. Instead, it gets catapulted away at nearly the speed of light, forming jets that stretch for millions of light years. Think of them as cosmic blowtorches, blasting through the galaxy with enough energy to strip planets bare or rip apart star systems in their path. The sheer power is staggering. A single quasar jet can travel so fast that if you could ride alongside it, time would slow down dramatically due to relativity. These beams carry particles accelerated to energies 1,000,000 times greater than anything we can produce in our most powerful particle colliders. And if one of those jets happened to point directly at Earth, even from billions of light years away, it could bathe our planet in lethal radiation, wiping out life in an instant. Yet, for all their destructive potential, quasars also play a crucial role in shaping the cosmos. Their jets heat surrounding gas, preventing it from collapsing into new stars, effectively putting a limit on how big a galaxy can grow. They're like cosmic regulators, ensuring the universe doesn't become overcrowded with stars. And in their violent hearts, they forge elements that will eventually seed new generations of planets and perhaps life. So while quasars are among the most lethal forces in existence, they're also architects of cosmic order, reminding us that even the universe's most violent events have a purpose. Black holes aren't always the stationary monsters we imagine. Some roam the cosmos like unstoppable predators, hurtling through galaxies at unimaginable speeds. These rogue black holes are the universe's ultimate drifters, ejected from their home systems by violent cosmic collisions, and now they travel alone, hungry and unchained. One such renegade was spotted racing through space at nearly 4 million miles per hour, fast enough to cross the distance from Earth to the Moon in under 15 minutes. What makes these wandering black holes so dangerous? Unlike their anchored counterparts, they don't stay put in galactic centers. They cut through star clusters, nebulae, and even solar systems, their immense gravity warping everything in their path. Picture a celestial wrecking ball. If a rogue black hole passed through our solar system, it wouldn't just disrupt planets' orbits, it could fling them into deep space or swallow them whole. And because black holes are invisible until they feed, their approach might go unnoticed until it's too late. How do these cosmic nomads break free? The answer lies in chaos. When galaxies collide, their central supermassive black holes often spiral toward each other, locked in a gravitational dance. But if a third black hole enters the mix, the balance shatters. One can get flung outward like a slingshot, stripped of its stellar neighborhood and set adrift. That's likely what happened to the runaway, clocked at 4 million miles per hour. Its speed so extreme it could escape the pull of even the largest galaxies. Yet for all their destructive potential, rogue black holes leave behind clues. As they plow through clouds of gas, their gravity compresses the material, triggering new star formation in their wake. It's a paradox these agents of chaos also create. Some astronomers even speculate that wandering black holes could seed life by scattering heavy elements across the cosmos. Still, you wouldn't want one nearby. Their appetite is insatiable, their paths unpredictable, and in the vast dark between stars, they move unseen, silent, relentless, and utterly unstoppable. Gamma-ray bursts are the universe's most extreme light shows, brief, blinding flashes that pack more punch than a supernova. In just a few seconds, a single burst can unleash more energy than our sun will emit over its entire 10 billion-year lifetime. These aren't just cosmic fireworks, they're apocalyptic explosions capable of sterilizing entire galaxies, and we've felt their effects firsthand. Take the gamma-ray burst of March 19, 2008. Detected 7.5 billion light-years away, it was so powerful that its afterglow remained visible to the naked eye for nearly a minute, something never before recorded in human history. But the real shock came when scientists realized it had physically disturbed Earth's upper atmosphere, briefly ionizing a layer of our planet's protective shield. What makes these bursts so devastating? Unlike hypernovas or quasars, gamma-ray bursts focus their energy into tight, laser-like beams. Imagine the sun's entire output squeezed into a narrow column of light thinner than a pencil, and then imagine that beam sweeping across space like a cosmic spotlight. Any planet caught in its path would face instant catastrophe. The radiation would shred ozone layers, trigger global acid rain, and bombard the surface with enough energy to ignite wildfires worldwide. Some researchers believe a nearby gamma-ray burst might have contributed to the Ordovician extinction 450 million years ago, wiping out nearly 85% of marine life. Yet for all their destructive potential, gamma-ray bursts also serve as cosmic lighthouses. Their incredible brightness allows astronomers to study the early universe, revealing galaxies so distant their light has traveled for over 13 billion years. They're even linked to the creation of heavy elements like gold and platinum, forged in the violent aftermath of colliding neutron stars, one of the few events energetic enough to produce a short gamma-ray burst. So while these flashes of annihilation remind us of space's capacity for violence, they also illuminate the universe's deepest secrets, proving once again that destruction and discovery are intertwined on the grandest scales. Right now, two cosmic giants are locked in a deadly embrace, the Milky Way and Andromeda, hurtling toward each other at 250,000 miles per hour. This isn't science fiction, it's an inevitable galactic collision set to unfold in about 4 billion years, and when these titans meet, the night sky as we know it will transform forever. Galactic mergers might sound violent, and they are, but they're also strangely beautiful. Unlike the chaotic explosions of supernovas or the ferocious jets of quasars, this collision will unfold in slow motion, a ballet of gravity and time. Stars won't crash into each other, space is too vast for that. Instead, their gravitational dance will fling entire solar systems into the void. Imagine a cosmic slingshot where stars are ripped from their galaxies and sent spiraling into the darkness, orphaned in intergalactic space. Some will be accelerated so fast they'll escape the combined galaxy's grip entirely, becoming lone wanderers in an empty sea of black. Simulations reveal just how stunning and destructive this event will be. As Andromeda's gravity distorts the Milky Way's spiral arms, vast streams of stars will stretch like taffy across the sky. The two black holes at their centers will spiral closer, kicking stars outward with each orbit until they finally merge, sending gravitational shockwaves rippling through the cosmos. The resulting galaxy, nicknamed Milkdromeda, will be a colossal, elliptical beast, no longer the graceful spiral we know today. Yet, amid this chaos, there's a twist. Despite the sheer scale of destruction, the odds of any two stars colliding are almost zero. Our solar system, it'll probably be flung farther from the galactic core, but the sun and planets will likely survive unscathed. That's the paradox of galactic collisions. They reshape entire universes while leaving individual worlds untouched. This merger isn't just a one-time event, it's part of a cycle. Galaxies grow by consuming others, and Andromeda itself bears the scars of past collisions, with ghostly trails of stars hinting at ancient conquests. In the end, even the violence of galactic collisions serves a purpose, building something new from the wreckage of the old. So while the Milky Way's fate is sealed, its legacy will live on, scattered, reshaped, but never truly gone. The sun might seem like a steady, unchanging presence in our sky, but beneath its calm surface lurks a potential apocalypse. Solar superflares are colossal eruptions of magnetic energy, capable of unleashing storms powerful enough to send civilization back to the Dark Ages. The most infamous example, the Carrington event of 1859, when a solar flare so intense it set telegraph wires on fire and lit up the night sky as far south as the Caribbean. But here's the terrifying truth: if a storm like that hit today, the damage wouldn't just be sparks and auroras. it would cripple the modern world. Modern power grids, satellites, and even undersea internet cables are vulnerable to these cosmic tantrums. A single superflare could induce electrical currents strong enough to melt transformers, knocking out power for months across entire continents. Imagine a world without refrigeration, communication, or running water, not for days but for years. NASA estimates the economic toll could reach into the trillions, with cascading failures destabilizing everything from banking systems to food distribution. And it's not just hypothetical. In 2012, a Carrington-level storm missed Earth by just 9 days. Had it struck, we'd still be picking up the pieces. What makes these solar storms so destructive? When the sun's tangled magnetic fields snap, they hurl billions of tons of charged particles into space at millions of miles per hour. If that tsunami of plasma hits Earth, it compresses our planet's magnetic field, shaking it like a snow globe. The resulting geomagnetic storm can turn power lines into antennas, funneling destructive currents into vulnerable infrastructure. Even buried fiber optic cables aren't safe. Their delicate repeaters, spaced every 50 miles, would fry under the assault. The irony: the more advanced our technology becomes, the more fragile we are to the sun's fury. In 1859, the damage was limited to telegraph machines. Today, a similar event could collapse supply chains, disrupt emergency services, and strand millions without transportation as GPS systems fail. Scientists warn we're overdue for another Carrington-level storm, with some estimates suggesting a 12% chance of one striking within the next decade. Yet there's hope. Early warning systems like NASA's Solar Dynamics Observatory can give us precious hours to shut down vulnerable systems before a storm hits. Governments are slowly hardening power grids, and engineers are designing satellites with better shielding, but the clock is ticking. The sun doesn't care about our preparations. It operates on its own timeline. And when it next unleashes its full fury, the world will hold its breath, waiting to see if our defenses are enough to weather the storm. Deep in the cosmos, 2 dead stars, each more massive than our sun but compressed into a sphere the size of a city, spiral toward each other at half the speed of light. Their dance is inevitable, their collision cataclysmic. This is a neutron-star merger, one of the universe's most violent and productive events. When these ultra-dense remnants of supernovas finally collide, they don't just crash, they detonate with the force of 1 billion nuclear bombs, shaking the very fabric of spacetime itself. And on August 17, 2017, humanity witnessed one firsthand. The event, dubbed GW170817, marked a turning point in astronomy. For the first time, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected the ripples in spacetime from the merger, while telescopes across the globe caught the blinding flash of light that followed. The data revealed something astonishing. In the chaos of that collision, a staggering amount of heavy elements were forged in seconds. We're talking about hundreds of Earth masses worth of gold, platinum, and uranium, enough to coat entire planets in a layer of precious metals. Here's how it happens. As the neutron stars tear into each other, their immense gravity rips them apart, ejecting a superheated jet of neutron-rich material. This cosmic debris is so dense that a single teaspoon would weigh billions of tons on Earth. In this extreme environment, atomic nuclei are bombarded with neutrons at an unimaginable rate, rapidly building heavier and heavier elements through a process called rapid neutron capture, or the R process. It's like a nuclear factory operating at warp speed, where ordinary matter is transformed into the rarest elements in the periodic table. But the real spectacle isn't just what's created, it's how it's scattered. The explosion hurls these newly minted elements into space at nearly light speed, seeding future generations of stars and planets with the building blocks of everything from jewelry to nuclear reactors. In fact, scientists now believe most of the gold in your wedding ring or smartphone was likely forged in a neutron star collision billions of years ago. GW170817 didn't just confirm a theory, it rewrote our understanding of cosmic alchemy. Before this detection, astronomers debated where heavy elements originated. Supernovas were the prime suspect, but their yields couldn't account for the abundance of gold and platinum in the universe. Neutron star mergers, once considered rare, now appear to be the universe's primary foundries for these precious metals. Yet for all their creative power, these events are also unfathomably destructive. The gravitational waves from GW170817 revealed that the merged neutron stars likely collapsed into a black hole almost instantly. The energy released was so immense that if it happened within a few thousand light-years of Earth, the resulting gamma-ray burst could have sterilized our planet. It's a stark reminder that the same forces that gift the cosmos with gold are also capable of cosmic-scale annihilation. What's next? Astronomers are now hunting for more of these mergers, using gravitational waves as their guide. Each detection peels back another layer of the mystery, revealing how the universe transforms the debris of dead stars into the elements that make life possible. So the next time you hold a piece of gold, remember, it wasn't forged in the heart of a star, but in the violent aftermath of a collision so powerful it bent the fabric of reality itself. There's a theory so unsettling it keeps physicists awake at night, the idea that our universe might not just end with a bang or a whimper, but with a silent, instantaneous rewrite of reality itself. This is vacuum decay, a quantum doomsday scenario where the fundamental laws of physics could unravel in the blink of an eye. Picture this: somewhere in the depths of space, a tiny bubble forms where the rules we take for granted, like gravity or electromagnetism, suddenly shift. This bubble expands at the speed of light, rewriting everything in its path. One moment, stars, planets, and life exist. The next, they're erased, replaced by a new reality where atoms can't even hold together. What makes vacuum decay so chilling is its inevitability. If it's possible, it's already happened. The universe's current state might be a false vacuum, a precarious balance that could collapse into a more stable configuration at any moment. Think of it like a marble resting on the edge of a bowl. It's stable for now, but the slightest nudge could send it rolling into the bowl's base, a lower energy state where the rules change entirely. In cosmic terms, that nudge could be a random quantum fluctuation, sparking a chain reaction that consumes the cosmos. Here's the twist: we wouldn't see it coming. The bubble's boundary would move at light speed, giving no warning. By the time the edge reached Earth, our planet and every memory, invention, and civilization would vanish mid-thought, erased so completely it's as though we never existed. Even light from the event couldn't outrun the destruction, meaning telescopes wouldn't spot it until it was already upon us. But there's a bizarre silver lining. If vacuum decay occurred, the new physics inside the bubble might allow for entirely unknown forms of matter or energy realities where life could evolve in ways we can't fathom. Some theorists even suggest this process could be responsible for the universe's initial conditions, meaning our existence might owe itself to an ancient vacuum decay event in a predecessor universe. For now, vacuum decay remains a terrifying what-if. No evidence suggests it's imminent, and the universe's 14-billion-year track record hints our vacuum is stable for now. Yet the mere possibility reminds us how fragile reality might be, built on rules that could change without notice. It's the ultimate cosmic gamble. Every second we exist, we're betting the laws of physics won't suddenly decide to play by new ones. Deep in the void between galaxies, an invisible killer might lurk: dark matter, the mysterious substance that makes up 85% of the universe's mass. We can't see it, touch it, or detect it directly, yet its gravity shapes galaxies and bends space-time itself. But what if this cosmic ghost isn't just passively floating through space? What if, under the right conditions, dark matter could annihilate itself in bursts of lethal radiation capable of sterilizing entire star systems? Scientists call this phenomenon dark matter annihilation, and while it's purely theoretical, the mechanics are spine-chilling. Here's how it might work. If certain types of dark matter particles collide, they could obliterate each other in a flash of gamma rays, X-rays, or other high-energy radiation. Picture two invisible bullets striking midair and detonating with the force of a nuclear bomb, except these bullets are particles so tiny, trillions could pass through your body every second without you noticing. Now imagine them igniting in the heart of a galaxy, unleashing a radiation storm fierce enough to strip away atmospheres or mutate DNA across light years of space. The most terrifying part, we might never see it coming. Dark matter doesn't interact with light, so these annihilation fronts could sweep through a region of space undetected until the radiation reaches a planet. Some theories even suggest that past extinction events on Earth, like the mysterious disappearance of the dinosaurs, could have been triggered by a nearby dark matter flare. While there's no direct evidence for this, the math is unsettling. If dense clumps of dark matter exist in our galactic neighborhood, their collisions could produce radiation spikes powerful enough to disrupt ecosystems. Yet annihilation isn't just a doomsday scenario. It's also a tantalizing clue for solving one of physics' greatest mysteries. Telescopes like the Fermi Gamma Ray Space Telescope hunt for unexplained gamma-ray signatures that might reveal dark matter's presence. In 2015, scientists detected an eerie excess of gamma rays coming from the center of our galaxy, a region teeming with dark matter. Could this be the smoking gun of annihilation? Or just the glow of mundane cosmic phenomena like pulsars? The debate rages on. What makes dark matter annihilation so fascinating is its duality. It's both a potential apocalypse and a beacon of discovery. If proven real, it would finally give us a window into the invisible scaffolding of the universe, confirming decades of theoretical work. But it would also remind us that the cosmos is far from benign. Even the unseen forces holding galaxies together might harbor a destructive edge lurking in the shadows until the moment they ignite. So while we search for answers, one truth remains: the universe's greatest threats aren't always the ones we can see. Sometimes they're the ghosts hiding in plain sight, waiting for the right conditions to reveal their power. And whether dark matter annihilation is a reality or just a cosmic what if, it forces us to confront a humbling idea that the unknown might be just as dangerous as it is mysterious. Hidden in the darkness of space, some of the deadliest objects in existence don't explode, they crack. Magnetars, the universe's most powerful magnets, are neutron stars with magnetic fields so intense they could strip the data from every credit card on Earth from halfway across the galaxy. But what makes them truly terrifying isn't just their magnetism, it's their ability to unleash starquakes so violent they warp spacetime itself. Imagine a stellar corpse with the mass of a sun crammed into a ball just 12 miles wide. The crust of a magnetar isn't like Earth's brittle surface, it's a lattice of ultra-dense nuclear matter, a crystalline shell under unimaginable strain. And when that shell finally gives way, the result is a cataclysm called a starquake. The energy released dwarfs anything in our solar system, equivalent to a magnitude 32 earthquake, hundreds of billions of times stronger than the most powerful quake ever recorded on Earth. But a magnetar's quake doesn't just shake the star, it snaps its magnetic field lines like rubber bands, whipping them into a frenzy. The recoil sends torrents of X-rays and gamma rays screaming into space. In 2004, a magnetar 50,000 light-years away unleashed a blast so bright it blinded satellites and ionized Earth's upper atmosphere, all from halfway across the Milky Way. If that same quake had happened within 10 light-years of us, the radiation could have triggered mass extinctions. Here's where it gets even wilder. These quakes don't just emit radiation, they literally bend the fabric of reality. The sudden shift in the star's crust sends ripples through spacetime itself, gravitational waves detectable across the cosmos. Scientists compare it to hitting a gong with a sledgehammer. the vibrations echo across the universe, carrying secrets about the strange matter inside these extreme objects. Yet for all their destructive power, magnetar starquakes are also cosmic gold mines. The flashes of radiation contain clues about physics under conditions impossible to recreate on Earth, where matter is so dense a single sugar cube-sized chunk would weigh billions of tons. Some researchers even speculate that these events could be the mysterious source of fast radio bursts, those enigmatic deep space signals that have puzzled astronomers for years. So while we're safe from the immediate threat, no known magnetar is close enough to sterilize Earth. These starquakes remind us that the universe is far from static. Even dead stars can wake in violent upheavals, cracking open to reveal the ferocious forces churning beneath their surfaces. And with each quake, they send a message. In the cosmos, destruction and discovery are two sides of the same coin. In the first sliver of a second after the Big Bang, the universe didn't just expand, it exploded outward at a speed so incomprehensible it defies all intuition. This was cosmic inflation, a period where space itself stretched faster than light, doubling in size at least 90 times in less time than it takes light to cross a single proton. To grasp the sheer violence of this process, imagine taking an entire galaxy and stretching it to the size of the observable universe, not over billions of years, but in a fraction of a blink. This wasn't gentle growth, it was a runaway reaction so extreme that any structure, no matter how resilient, would have been obliterated instantly. Atoms, molecules, even the fabric of spacetime itself were stretched thinner than thought itself could follow. If by some miracle a planet-sized object had formed in those first moments, inflation would have shredded it down to its fundamental particles before it could complete a single rotation. The forces at work here make supernovas look like firecrackers. This was the universe tearing itself apart to create itself anew. Why such chaos? The driving force was a mysterious energy field called the inflaton, which dominated the cosmos with repulsive gravity. Picture a ball rolling down an endless hill, except the hill is made of anti-gravity. The further the ball rolls, the harder it pushes outward, accelerating the expansion exponentially. When this field finally collapsed, it dumped all that pent-up energy into the universe, reheating it into the seething plasma of the hot Big Bang. But here's the twist: inflation didn't just destroy, it also planted the seeds for everything to come. Quantum fluctuations in that field, magnified to cosmic scales, became the blueprints for galaxies and galaxy clusters. The echoes of this cataclysm are still with us today. Without inflation's violent smoothing, the universe would be a jagged wasteland of black holes and empty voids. It's a paradoxical legacy, a moment of ultimate destruction that made creation possible. So while no structure could survive inflation's fury, we owe our existence to the very forces that ensured nothing could. Picture a cosmic particle accelerator so powerful it can fling matter across galaxies at nearly the speed of light. Now imagine that accelerator isn't some delicate human machine, but a screaming jet of plasma blasting from the maw of a black hole. These are relativistic jets, nature's ultimate death rays, stretching for thousands of light years and packing enough energy to outshine entire star systems. Take Cygnus X1, a black hole just 6,000 light years from Earth, where gas spiraling toward oblivion doesn't just vanish. It gets catapulted into space in twin beams hot enough to vaporize planets. What makes these jets so astonishing isn't just their speed, it's how they form. As matter falls toward a black hole, friction heats it to millions of degrees, creating a swirling disk of supercharged plasma. But not all that material crosses the event horizon. Some gets caught in the black hole's twisted magnetic fields, channeled toward its poles like water forced through a fire hose. There, the black hole's rotation acts like a cosmic slingshot, accelerating particles to velocities so extreme that time dilation kicks in. For an electron riding that jet, minutes could pass while years crawl by elsewhere in the universe. Cygnus X1's jets aren't just fast, they're galactic-scale blowtorches. The energy they release in X-rays and gamma rays is so intense, astronomers detect them across interstellar distances. If you could stand near one, a suicidal thought experiment, the radiation would rip you apart atom by atom before your nerves could register pain. Yet these lethal beams also shape their surroundings in unexpected ways. When they plow into clouds of gas, they trigger shock waves that compress material, sparking new star formation. It's a paradox. The same forces that obliterate matter also sculpt nurseries for future suns. The true marvel scale. Some supermassive black holes produce jets stretching millions of light years, far larger than their host galaxies. These aren't just local phenomena. They're intergalactic lightning bolts capable of heating gas in neighboring galaxy clusters and stifling star birth across cosmic volumes. And because they're so narrow, often no wider than a solar system despite their length, their energy stays focused over incomprehensible distances. A single jet from a distant quasar can remain pencil-thin for hundreds of thousands of light years, like a laser pointer aimed with godlike precision. Yet for all their destructive potential, relativistic jets are also cosmic Rosetta Stones. By studying their light, scientists decode the physics of black hole spin, plasma behavior under extreme conditions, even the nature of spacetime itself. Cygnus X1's jets recently revealed something shocking: black holes may not just consume matter, but also recycle it, spewing enriched particles back into the galaxy. So while these beams are born from violence, they might just be the universe's way of stirring the pot, ensuring no corner of space remains untouched by change. The concept of false vacuum decay isn't just terrifying, it's dimensionally deceptive. Most discussions focus on how a vacuum bubble could expand at light speed through our three-dimensional universe, erasing reality as it goes. But here's the twist: if higher dimensions exist, as string theory suggests, the collapse might already be underway in realms we can't perceive. Imagine a crack spreading through ice. You only see the surface fracture, while the damage runs far deeper beneath. Similarly, a false vacuum event could originate in a dimension beyond our observational reach, its catastrophic effects leaking into our universe only when it's too late to react. How would this multidimensional doomsday unfold? In our familiar spacetime, a vacuum bubble would form due to a quantum fluctuation, then expand relentlessly, rewriting physical laws at its boundary. But in higher dimensional models, the bubble could propagate through additional spatial dimensions we can't access or measure. Think of it like an ant on a table detecting a spreading stain. It sees the two-dimensional spread but remains oblivious to the liquid dripping from above until the entire surface is soaked. By the time our instruments registered the anomaly, the collapse front might already be intersecting our universe at multiple points, surrounding us like an inescapable net. The real horror lies in the physics. If extra dimensions exist, they could lower the energy barrier needed to trigger vacuum decay, making catastrophe far more likely than we've calculated. Some theoretical models suggest that what we perceive as a stable universe might actually be teetering on the edge of a higher dimensional cliff, one random quantum event away from annihilation. Even more unsettling, the bubble's expansion could exploit higher dimensional geometry to tunnel through barriers our 3D math says should contain it, like a ghost passing through walls. Yet there's a bizarre counterpoint to this doom. Some physicists speculate that if we ever detected signs of vacuum decay, say through sudden shifts in fundamental constants, it might reveal the hidden architecture of extra dimensions before the end. Like hearing the creaks of a collapsing building moments before it falls, these anomalies could offer humanity a fleeting glimpse into the multidimensional fabric of reality. So while we scan the cosmos for black holes and supernova, the ultimate threat might not come from anything we can see, but from a silent, invisible unraveling in the dimensions beyond our grasp. And in that uncertainty lies perhaps the most humbling truth of all. The universe's deadliest dangers may not even announce themselves until the very last moment. Imagine a star catapulted from the heart of a galaxy at speeds that defy reason, 2 million miles per hour, fast enough to cross the distance from Earth to the Moon in just 45 minutes. This isn't science fiction, it's the reality of hypervelocity stars, cosmic fugitives flung into the void by some of the universe's most brutal forces. Take He 0437-5439, a rogue star discovered streaking through intergalactic space at a staggering 1.6 million miles per hour. Its crime, getting too close to the supermassive black hole at the Milky Way's core. Here's how these stellar outlaws break free. When a binary star system, two stars orbiting each other, wanders into the gravitational kill zone of a supermassive black hole, the results are catastrophic. The black hole's immense gravity rips the pair apart, capturing one star while violently ejecting the other like a slingshot. The energy of this cosmic heist is so extreme that the ejected star doesn't just escape the black hole, it escapes the galaxy entirely, destined to drift alone through the freezing darkness between galaxies. He 0437-5439 is one such exile, already over 160,000 light-years from home and still accelerating. But speed isn't the only mystery here. This star shouldn't exist. Based on its velocity and trajectory, astronomers calculated it would have taken 100 million years to reach its current position, yet spectral analysis reveals it's only 35 million years old. How does a star arrive somewhere faster than physics allows? The answer might lie in a three-body tango with the Milky Way's central black hole, where multiple gravitational kicks could have supercharged its escape. Alternatively, it could be a blue straggler, a stellar Frankenstein forged from the merger of two older stars, resetting its age clock while preserving its momentum. The aftermath of these ejections is just as fascinating as the event itself. Hypervelocity stars don't just vanish, they leave ghostly trails of heated gas and disrupted orbits in their wake. Some even trigger shockwaves as they plow through interstellar clouds, compressing material into new star-forming regions. It's a cosmic irony. These stars, condemned to eternal solitude, might inadvertently sow the seeds for future solar systems as they blaze through the void. Yet their greatest value lies in what they reveal about the universe. By tracing the paths of hypervelocity stars, astronomers can map the hidden gravitational landscape of galaxies, including the distribution of dark matter. These stellar speedsters act like probes, their trajectories warped by invisible masses we can't otherwise detect. And because they're flung from galactic cores, studying their composition offers a rare glimpse into the extreme environments near supermassive black holes, places too hostile for direct observation. So while He 0437-5439 may never find a new home, its solitary journey is anything but pointless. It carries with it the secrets of gravitational monsters, the architecture of space-time, and the relentless dynamism of a universe that refuses to let anything, not even a star, stay in one place forever. When two neutron stars collide, they don't just create gold and platinum. They forge the universe's most dangerous elements. Kilonovas, the violent aftermath of these mergers, act as cosmic foundries, scattering uranium and plutonium across interstellar space like radioactive shrapnel. These aren't just heavy metals, they're the unstable fuel for future cosmic detonations, ticking time bombs hidden in the dust of newborn star systems. Take the kilonova GW170817, where scientists detected traces of uranium-rich debris expanding at 5% the speed of light. That material didn't just drift aimlessly, it became part of vast interstellar clouds, eventually collapsing into new generations of stars. But here's the catch: when those stars eventually die in supernovas, their uranium-rich cores can trigger even more violent explosions. It's a chain reaction of destruction, where the remnants of one cosmic collision set the stage for the next. The process works like this. As neutron stars merge, their incredible density and heat create conditions perfect for rapid neutron capture, or the R process. This nuclear alchemy doesn't stop at stable elements like gold. It builds unstable isotopes like uranium-238 with half-lives measuring billions of years. These elements get blasted outward in the kilonova's ejector, mixed with lighter materials in a radioactive cocktail. Over millions of years, this debris becomes part of molecular clouds where gravity pulls it into new stellar systems. But uranium isn't a passive ingredient, it's a catalyst for chaos. When incorporated into a massive star's core, its radioactive decay generates extra heat, altering the star's internal dynamics. Some models suggest this added energy might make supernovas more asymmetric, increasing the chances of forming hypervelocity neutron stars or even rogue black holes. Worse yet, in rare cases, concentrated uranium deposits in a star's core could trigger premature detonations, like a cosmic dirty bomb hidden in the heart of a sun. Yet for all their destructive potential, these elements also play a paradoxical role in shaping habitable worlds. Uranium's radioactive decay in planetary cores provides geothermal energy, driving plate tectonics and volcanic activity processes essential for maintaining Earth-like atmospheres. Without kilonovas seeding the galaxy with heavy, unstable elements, planets might lack the internal heat to sustain magnetic fields or recycle nutrients through their crusts. The frightening truth, we're surrounded by the fallout from these ancient explosions. Trace amounts of uranium in Earth's crust, and even in our bodies, likely originated in a kilonova that detonated billions of years before our solar system formed. Every nuclear reactor, every atomic weapon, even the natural fission reactors found in prehistoric Oklo, Gabon, owe their existence to a cataclysm so violent it helped shape the periodic table itself. So while kilonovas might seem like distant, inconsequential events, their radioactive legacy lingers everywhere. They're proof that destruction and creation are inseparable, that the same forces capable of sterilizing star systems also provide the tools for life to rebuild. And somewhere out there, another neutron star merger is brewing, its uranium payload waiting to ignite the next cycle of cosmic death and rebirth. Buried at the heart of nearly every massive galaxy lies a ravenous beast, an active galactic nucleus, powered by a supermassive black hole so voracious it can outshine every star in its host galaxy combined. These aren't just black holes idly snacking on passing gas. They're full-blown cosmic furnaces capable of shining with the brilliance of 1 trillion suns for millions of years. The most extreme example, Quasar 3278029, a monstrosity so luminous its light traveled 12 billion years to reach us, making it visible despite being older than Earth itself. What transforms an otherwise invisible black hole into such a dazzling spectacle? It all comes down to the physics of destruction on an unimaginable scale. As cosmic debris, gas, dust, even entire stars spirals toward the event horizon, friction heats the material to billions of degrees, creating a swirling disk of white-hot plasma. This isn't just hot, it's hotter than the core of a supernova, emitting enough X-rays to sterilize planets thousands of light-years away. But the real magic happens when magnetic fields channel some of that doomed matter into jets, shooting it back into space at nearly light speed. These jets can stretch for millions of light-years, forming visible structures larger than the galaxies they originate from. The energy output defies belief. Quasar 3278029 radiates 1,000 times more energy than our entire Milky Way, all from a region no larger than our solar system. That's like cramming the power of a hurricane into a teacup. Some active nuclei are so bright they drown out their host galaxies completely, appearing as single points of light indistinguishable from stars until you analyze their spectra and realize you're looking at the equivalent of 1 million supernovas screaming in unison. Yet these cosmic beacons aren't just destructive, they're also galactic sculptors. The intense radiation and powerful jets heat surrounding gas, preventing it from cooling and forming new stars. In effect, active galactic nuclei act as cosmic thermostats regulating galaxy growth. Without them, the universe might be overrun with stars, leaving no room for the vast voids that give the cosmos its structure. They're proof that even the most violent forces can impose order, balancing creation and annihilation on scales we're only beginning to comprehend. The terrifying beauty of these phenomena is their longevity. While supernovas fade in weeks and gamma-ray bursts last mere seconds, active galactic nuclei can shine for hundreds of millions of years, a slow, sustained eruption of energy that rewrites the destiny of everything around them. And when they finally quiet down, they leave behind a changed universe where the echoes of their fury become the building blocks of new cosmic cycles. Some of the universe's most terrifying weapons aren't explosions or collisions, they're defects in the very fabric of reality itself. Cosmic strings, hypothetical cracks in space-time leftover from the Big Bang, are thought to be thinner than a proton yet denser than a mountain range, stretching across the cosmos like invisible razor wires. If one were to pass through Earth, it wouldn't just cut through rock and metal, it would slice through atoms themselves, cleaving our planet apart with the ease of a scalpel through tissue paper. These bizarre structures aren't black holes or dark matter, they're something far stranger. Picture the universe in its first moments, a seething, chaotic broth of energy. As it cooled, cracks might have formed in space-time, much like flaws appearing in ice as it freezes. These cracks, cosmic strings, would be under unimaginable tension, with just a single-mile-long segment containing more mass than all the stars in our galaxy combined. And because they're defects in space-time itself, they don't obey the laws of physics as we know them. A cosmic string could move at nearly the speed of light, warping space around it so severely that if two strings crossed, they might create a time loop or even spawn a brand new universe. The destruction they could unleash is almost too bizarre to fathom. A string's gravitational field isn't like a planet's or a star's, it's more like a knife's edge. Anything passing near it wouldn't just be pulled inward, it would be sheared apart by tidal forces so extreme they'd make a black hole's spaghettification look gentle. If a string grazed our solar system, its gravity could fling planets out of orbit like billiard balls, or worse, slice the sun in half without slowing down. Some theories suggest these strings might even be behind mysterious phenomena like double images of distant quasars, where their space-time warping effects bend light like a funhouse mirror. Yet for all their destructive potential, cosmic strings could also be the universe's ultimate cosmic scribes. Their unimaginable energy might seed the formation of galaxies, their gravitational wakes acting as blueprints for the vast webs of matter we see today. Some physicists even speculate that if we could detect a string's unique gravitational wave signature, it would offer a direct window into the universe's first trillionth of a second, a relic from a time before time itself had fully formed. So while we've yet to find definitive proof of these space-time scars, their mere possibility reminds us that the universe's earliest moments might have left behind more than just light and matter. Hidden in the darkness between galaxies, there could be flaws so sharp they cut through dimensions, silent, ancient, and infinitely deadly. And if they're real, they're proof that the fabric of reality isn't just fragile, it's got edges. Deep in the cosmos, a stellar corpse is about to commit the ultimate comeback. A white dwarf, the burnt-out remnant of a sun-like star, suddenly explodes with the force of 100 billion suns. This is a Type Ia supernova, one of the most precise and predictable cosmic explosions in the universe. But what makes these events so extraordinary isn't just their violence, it's how they happen. A white dwarf is already dead, its nuclear fuel exhausted, compressed into a dense Earth-sized sphere of carbon and oxygen. Yet under the right conditions, this cold, dark ember can reignite with apocalyptic fury, becoming the universe's ultimate standard candle. The trigger, a fatal partnership. Most white dwarfs fade quietly into darkness, but if one orbits close enough to a companion star, perhaps a red giant or even another white dwarf, it can begin siphoning material onto its surface. Slowly, agonizingly, this stolen matter builds up until the dwarf reaches a critical threshold, 1.4 times the mass of our Sun. At that precise moment, the pressure in its core becomes so intense that carbon atoms, normally stable, suddenly begin fusing uncontrollably. In less than a second, a runaway nuclear chain reaction rips through the star like wildfire through dry grass. The entire white dwarf doesn't just explode, it detonates with such uniformity that these blasts are nearly identical across the universe, like cosmic atomic clocks set to the same alarm. This uniformity is what makes Type Ia supernovas so invaluable to astronomers. Because they always explode at the same critical mass, their peak brightness is virtually identical, allowing scientists to calculate their distance with remarkable accuracy. It's like having a series of identical light bulbs scattered across the cosmos. By measuring how dim they appear from Earth, we can map the scale of the universe itself. In the late 1990s, observations of distant Type Ia supernovas led to the shocking discovery that the universe isn't just expanding, it's accelerating, propelled by a mysterious force we now call dark energy. Without these dead star explosions, we might never have uncovered one of cosmology's greatest mysteries. But the aftermath of a Type Ia supernova is just as fascinating as the explosion itself. Unlike the messy remnants left by core-collapse supernovas, these events leave virtually nothing behind, just an expanding cloud of iron, silicon, and nickel hurled into space at thousands of miles per second. The iron in your blood, the calcium in your bones, even the silicon in your smartphone, much of it was forged in these catastrophic detonations. Some models suggest a single Type Ia supernova can produce an entire Earth's worth of iron in seconds, scattering it across light years of space to eventually become part of new stars, planets, and perhaps even life. Yet for all their destructive power, these explosions also have a strange kind of elegance. The physics is so precise that even slight variations, like a slightly off-center ignition or a dwarf that spins too fast, can dramatically alter the outcome. Some may fail to detonate completely, resulting in bizarre hybrid stars or even zombie white dwarfs that survive multiple near explosions. Others might produce unusually faint or bright supernovas, challenging our assumptions about these cosmic yardsticks. Each deviation is a clue, helping refine our understanding of stellar death and the forces that shape the cosmos. So the next time you look up at the night sky, remember, some of those twinkling lights aren't stars at all, but the ghosts of white dwarfs that chose to go out in a blaze of glory, precise, predictable, and powerful enough to illuminate the darkest corners of the universe. Black holes don't just swallow matter, they play a cruel game of cosmic torture first. The process has a deceptively playful name, spaghettification. But there's nothing whimsical about what happens when an object drifts too close to a black hole's event horizon. Imagine your feet first falling toward a stellar mass black hole. At first, nothing seems unusual until the tidal forces take hold. Your legs, being slightly closer to the black hole, feel a stronger gravitational pull than your head. The difference might start small, but it grows exponentially. Within seconds, you're not just falling, you're being stretched like taffy, elongated into a strand of atoms thinner than a human hair. This grotesque transformation isn't unique to unlucky astronauts. Stars suffer the same fate. When a star wanders too close, the black hole's gravity peels it apart layer by layer in a process called a tidal disruption event. Telescopes have captured these gruesome stellar deaths, a star's outer layers torn into a swirling stream of plasma, wrapping around the black hole like water circling a drain. The friction heats the material to millions of degrees, creating an X-ray flare so bright we can spot it from billions of light years away. But here's where physics gets truly bizarre. The severity of spaghettification depends on the black hole's size. Counterintuitively, smaller black holes are far more lethal. A stellar mass black hole, say, 10 times the Sun's mass, has such an intense gravitational gradient that it will shred you long before you cross the event horizon. But with a supermassive black hole like Sagittarius, a star at the Milky Way center, the tidal forces are gentler. You might actually cross the event horizon intact, only to face an even stranger doom as time and space warp beyond recognition. The aftermath of spaghettification is just as unsettling. Those stretched-out atomic strands don't vanish. They spiral into the black hole's accretion disk, adding to the swirling maelstrom of superheated matter. Some particles get flung outward in relativistic jets, while others vanish forever behind the event horizon. It's a reminder that in the universe's most extreme environments, even destruction follows rules written in the language of gravity, velocity, and the eerie geometry of spacetime itself. Right now, our universe isn't just expanding, it's accelerating, fueled by a mysterious force called dark energy. And if this relentless expansion continues unchecked, it won't just push galaxies apart, it will tear the very fabric of reality apart in a cataclysm known as the Big Rip. Picture this: billions of years from now, as dark energy's grip tightens, galaxy clusters will first drift into isolation. Then, individual galaxies themselves will unravel, stars wrenched from their orbits and flung into the void. But the horror doesn't stop there. In the final moments, planetary systems will disintegrate, planets torn from their suns. Then, in a last grotesque act of cosmic violence, even atoms will be ripped apart, nuclei shredded as the relentless expansion overcomes the very forces holding matter together. What makes this scenario so chilling isn't just the scale of destruction, it's the inevitability. Unlike stellar explosions or black hole collisions, the Big Rip isn't a localized event. There's no escaping it, no safe corner of the universe to hide. Dark energy operates everywhere at once, a silent, omnipresent force reshaping the destiny of everything. Current estimates suggest this ultimate unraveling could happen in as little as 22 billion years, a heartbeat in cosmic terms. Yet there's a strange beauty in the physics behind this apocalypse. The Big Rip occurs if dark energy's strength increases over time, a property called phantom energy. Unlike ordinary dark energy, which maintains a constant density as the universe expands, phantom energy grows denser, amplifying its destructive power. It's as if the universe is digging its own grave, each passing moment making the final rupture more violent. Astronomers have already glimpsed dark energy's fingerprints in the way distant supernovas fade faster than expected, their light stretched by the accelerating expansion. But whether this acceleration will culminate in a Big Rip depends on dark energy's exact nature, something we're still struggling to understand. Some theories suggest the rip could be avoided if dark energy weakens or transitions into another form. Others propose even more bizarre fates, like a Big Crunch, where the universe reverses course and collapses back into a singularity. For now, the Big Rip remains one of cosmology's most unsettling possibilities. A reminder that the universe's greatest threats aren't always fiery explosions or collisions, but the slow, inexorable forces hiding in empty space itself. And while humanity won't be around to witness it, the very fact that such an end is possible reshapes how we see our place in the cosmos. We're not just living in a universe that expands, we're riding a wave that might one day consume everything. Pulsars are nature's perfect lighthouses, except their beams don't guide ships to safety. They scorch everything in their path. Imagine a rapidly spinning neutron star, barely the size of a city but packing more mass than our sun, whipping around so fast it completes hundreds of rotations every second. Now imagine that this cosmic dynamo emits beams of radiation so focused and powerful they could slice through planetary atmospheres like a blowtorch through paper. That's the reality of pulsar death rays, a phenomenon where the universe's most precise cosmic weapons silently sweep through space, sterilizing entire star systems without warning. Take PSRB 1937 + 21, the fastest spinning pulsar known. It rotates at a mind-bending 642 times per second, its twin beams of X-rays and gamma rays carving through space with surgical precision. If a planet were unfortunate enough to drift into the path of those beams, the results would be apocalyptic. The radiation would strip away the ozone layer in minutes, bombard the surface with enough energy to ignite global wildfires, and bathe every living organism in lethal doses of ionizing radiation. And because pulsars can remain active for millions of years, any planet caught in their crosshairs would face repeated blasts, ensuring no chance for life to recover. What makes pulsars so deadly isn't just their radiation, it's their aim. Unlike supernovas or gamma-ray bursts, which unleash energy in all directions, pulsars focus their destruction into narrow cones, often no wider than a few degrees. These beams sweep across space like the spinning blades of a cosmic fan, hitting targets thousands of light-years away with pinpoint accuracy. Astronomers have even detected black widow pulsar systems where the neutron star's beams have vaporized a once-orbiting companion star, leaving behind nothing but a ghostly trail of ionized gas. The physics behind these death rays is just as fascinating as their destructive potential. Pulsars are born from the collapsed cores of massive stars, their intense magnetic fields channeling particles along their poles. As those particles accelerate to near light speed, they emit radiation in a process called curvature radiation, creating beams so intense they can outshine their host galaxy in radio waves. And because pulsars rotate with such stability, their beams arrive like clockwork, some pulsing with a regularity rivaling atomic clocks. Yet for all their lethality, pulsars also serve as cosmic laboratories. By studying their precise pulses, scientists have tested Einstein's theory of general relativity, mapped the structure of our galaxy, and even discovered the first exoplanets. Their beams act like interstellar sonar, revealing the density and magnetic fields of the space they traverse. Some researchers speculate that advanced civilizations might one day harness pulsar signals as navigation beacons, assuming they can avoid the deadly sweep of those radiation jets. So while pulsars may be among the universe's most efficient killers, they're also invaluable tools, reminding us that even the darkest forces in space can illuminate our understanding of the cosmos. Their deadly precision is a double-edged sword capable of obliterating worlds, yet sharp enough to carve new paths for discovery. Hidden in the darkness between planets, or even woven into the fabric of Earth itself, there could be relics from the universe's birth, primordial black holes, smaller than atoms yet heavier than mountains. These aren't the colossal monsters we're used to hearing about. These are hypothetical leftovers from the Big Bang, when the newborn universe's turbulent energy might have collapsed into ultra-dense knots so tight they formed black holes instantly. Some could be as light as a paperclip crammed into a space a billion times smaller than a proton, and if they exist, they might still be here, drifting unseen through our solar system. What makes these ancient specks of destruction so eerie is their elusiveness. A primordial black hole with the mass of an asteroid could pass straight through Earth without anyone noticing, its gravitational pull too weak to disturb tides or orbits, its size too tiny to block starlight. Only if it happened to collide with a dense object like a neutron star might we detect the tremors. Some theories even suggest these black holes could be lurking in the sun's core, slowly devouring it from within like invisible parasites. If that's true, our star's lifespan might be shorter than we think, its energy siphoned away by a relic older than time itself. But here's where it gets stranger. If these black holes are out there, they might not be completely dark. Thanks to Hawking radiation, the tiniest ones could be evaporating explosively, ending their lives in bursts of gamma rays. A black hole the mass of a skyscraper, for instance, would be vanishing right now, its final moments unleashing energy rivaling a nuclear bomb. Astronomers have searched for these telltale flashes, unyielding, hoping to catch a glimpse of a dying black hole from the dawn of time. So far, no luck, but if they ever spot one, it would rewrite our understanding of cosmic history, proving the universe once birthed black holes in the chaos of creation. The most unsettling possibility, some primordial black holes might be massive enough to explain dark matter. If countless asteroid-sized black holes swarm the galaxy, their combined gravity could account for the invisible mass-bending stars and galaxies. It's a haunting thought. The missing piece of the universe's puzzle might not be an exotic particle, but a sea of ancient black holes, remnants of a time when reality was forged in fire. Until we find proof, they remain ghosts in the cosmic machine, silent, enigmatic, and perhaps closer than we dare imagine. Galaxies aren't just islands of stars, they're cosmic engines capable of self-destruction. In the heart of starburst galaxies, where stars form at a frenzied rate hundreds of times faster than in our Milky Way, the sheer intensity of creation triggers an equally violent counter-reaction: galactic superwinds. These aren't gentle breezes, they're supersonic tsunamis of gas, screaming outward at 2,000 kilometers per second, fast enough to cross the entire United States in less than 2 seconds. And their purpose is as brutal as their speed: to starve the galaxy that birthed them. Picture a factory operating at maximum capacity, its machinery redlining as it churns out products non-stop. That's a starburst galaxy overloaded with young, massive stars burning through their fuel in mere millions of years. But these stars don't fade quietly. They die in spectacular supernovas, their explosions pumping energy into surrounding gas like a bellows stoking a fire. Soon, the cumulative force of thousands of these detonations creates pressure too immense to contain. The gas erupts outward in a shockwave so powerful it can blow an entire galaxy's worth of star-forming material into intergalactic space. The consequences are catastrophic and strangely beautiful. As the superwind rages, it carries with it not just raw hydrogen and helium, but heavy elements forged in stellar cores: carbon, oxygen, iron. These elements, which should have been recycled into new stars and planets, are instead hurled into the void, leaving behind a galactic wasteland. In the Antennae galaxies, a pair of colliding starburst systems observed by the Hubble Space Telescope superwinds have already ejected enough gas to build billions of stars, quenching star formation across regions spanning tens of thousands of light years. Yet these winds aren't just agents of destruction. By scattering enriched material across the cosmos, they seed future generations of galaxies with the building blocks for planets and life. Some of the iron in your blood, the calcium in your bones, might have once ridden a superwind from a galaxy far beyond our own. Even more remarkably, these outflows shape the universe on the largest scales. When superwinds from multiple galaxies collide in intergalactic space, they create vast reservoirs of hot gas known as the circumgalactic medium, a cosmic compost heap where future structures will take root. The irony is exquisite. The same violence that starves a galaxy of its potential also fertilizes the universe for new growth. Starburst galaxies, in their frenzied brilliance, become both executioners and midwives, their superwinds writing the next chapter of cosmic history even as they erase their own. And somewhere in the darkness, another superwind is gathering strength, a storm that will one day silence a galaxy's song of creation, only to whisper its echoes across the cosmos. At scales smaller than anything we can possibly observe, space itself is anything but empty or peaceful. It's a seething, frothing storm of quantum chaos. This is the realm of quantum foam, where the very fabric of reality churns with microscopic black holes, wormholes, and particles that flicker in and out of existence in less than a trillionth of a second. Here, at the Planck length, a distance so tiny that a single atom is gargantuan by comparison, the orderly universe we know dissolves into a turbulent ocean of creation and annihilation. Picture this: space-time isn't smooth like a calm lake. Instead, it's more like a boiling pot of water, bubbling with tiny, violent eruptions. these aren't just random fluctuations, they're full-blown micro-black holes appearing and vanishing so quickly they defy detection. Some theories suggest these fleeting black holes could even connect to other points in space or time through microscopic wormholes, creating a labyrinth of shortcuts through the cosmos. For an instant, a black hole smaller than a proton might form, swallowing a virtual particle pair before evaporating into nothingness, all before the universe even notices. The energy involved in this quantum frenzy is staggering. At these scales, the vacuum of space isn't empty, it's a battlefield where particles and antiparticles constantly duel, borrowing energy from the universe only to annihilate and repay the debt almost instantly. This is Heisenberg's uncertainty principle in action. The shorter the time, the more energy can fluctuate, and in the quantum foam, time intervals are so infinitesimal that space itself becomes a whirling storm of extreme physics. But what happens if these virtual black holes don't disappear? Some hypotheses suggest that in the extreme conditions of the early universe, quantum foam might have birthed primordial black holes, tiny yet potentially still lurking in space today. Others propose that these fluctuations could be the key to understanding wormholes, those hypothetical cosmic shortcuts that might one day allow interstellar travel. The most unsettling part, this quantum violence isn't confined to some distant realm. It's happening everywhere all the time. Right now, beneath your feet, inside the screen you're reading this on, space itself is a roiling foam of microscopic cataclysms. We don't notice it for the same reason we don't feel the individual vibrations of atoms. The chaos averages out into the smooth, predictable reality we experience. But zoom in far enough and the universe reveals its true nature, not a silent void, but a storm of creation and destruction playing out on the smallest scales imaginable. This raises a profound question: is the fabric of reality fundamentally stable, or is our orderly cosmos just the calm eye of an endless quantum hurricane? For now, we can only theorize, but one thing is certain: the universe is far stranger and far more violent than it appears. The sun isn't just a peaceful ball of light, it's a seething cauldron of plasma capable of hurling chunks of itself into space with the force of 1 billion nuclear bombs detonating at once. These eruptions, known as coronal mass ejections, are among the most violent phenomena in our solar system. When the sun's tangled magnetic field lines suddenly snap, they can catapult billions of tons of superheated plasma outward at speeds exceeding 2 million miles per hour, fast enough to reach Earth in less than a day. The sheer kinetic energy packed into these solar storms is staggering, equivalent to 10,000 times the world's total nuclear arsenal unleashed in a single, silent explosion. But we don't have to imagine the devastation these eruptions can cause. History has already shown us. In 1859, the Carrington event, the most powerful solar storm ever recorded, ignited telegraph wires, set paper aflame in operator stations, and painted the night sky with auroras so bright they turned night into day as far south as Cuba. Farmers woke thinking dawn had arrived at 2 in the morning, while gold miners in the Rocky Mountains began making breakfast, convinced by the crimson glow that the sun was rising. Today, a storm of that magnitude would do far worse than confuse sleep schedules. Modern power grids, acting as giant antennas for these geomagnetic disturbances, would surge with destructive currents, frying transformers and leaving continents in darkness for months. Satellite communications would fail, GPS systems would go haywire, and undersea internet cables, the backbone of global connectivity, could be rendered useless by induced currents. Scientists have recreated the Carrington event's conditions using supercomputer simulations, and the results are chilling. The storm's magnetic disturbance would induce currents in power lines strong enough to melt copper wiring, while the barrage of high-energy particles would degrade satellite electronics like sandblasting a circuit board. NASA estimates the economic impact could exceed $2 trillion in the first year alone, 20 times more costly than Hurricane Katrina. And the terrifying part: We're statistically overdue for another event of this scale. Ice core samples reveal that solar superstorms of Carrington magnitude strike Earth roughly once every 150 years, meaning we're living on borrowed time. Yet coronal mass ejections aren't just agents of destruction, they're also sculptors of planetary atmospheres. When these plasma clouds collide with worlds lacking magnetic fields, like Mars, they gradually strip away atmospheric gases, contributing to the planet's transformation from a wet, temperate world to the barren desert we see today. Earth's magnetic field largely protects us from this fate, but the protection comes at a cost. The very same magnetosphere that deflects these solar storms also funnels their energy toward the poles, creating the dazzling but potentially disruptive auroras we know. The paradox of these eruptions lies in their duality. They are both a clear and present danger to our technological civilization and a fundamental part of our cosmic environment. Without the Sun's occasional violent outbursts, Earth might never have developed the magnetic shield that makes complex life possible. And while we scramble to build early warning systems and hardened infrastructure, the Sun continues its turbulent dance, indifferent to our preparations. Each coronal mass ejection serves as a reminder that we're orbiting a star far more powerful and far less predictable than we often assume. Neutron stars aren't just cosmic corpses, they're ticking time bombs wrapped in a crust a billion times stronger than steel. And when that crust finally cracks under the strain, the results are catastrophic. Imagine a magnitude 32 earthquake, but instead of shaking for minutes, it unleashes all its energy in less than 1,000th of a second. That's the terrifying reality of neutron star quakes, where the tiniest shift in the star's surface unleashes more energy than our Sun radiates in 100,000 years. The physics behind these starquakes defies earthly comparison. A neutron star's crust is a crystalline lattice of atomic nuclei packed so tightly they form a near-impenetrable shell. But this isn't ordinary matter. It's hyper-dense material where a sugar cube's worth weighs as much as a mountain. When the star's ridiculous rotation, sometimes hundreds of times per second, warps its shape, the crust bends like a spoon pressed against a table. Eventually, the stress becomes too much. The crust snaps, shifting by mere centimeters. But in an object this dense, that tiny movement unleashes a seismic event beyond human comprehension. The resulting quake releases energy equivalent to 10 billion hydrogen bombs detonating simultaneously, shaking the entire star like a bell struck by a cosmic hammer. We've actually witnessed the aftermath of these events. In 1998, the neutron star SGR 1900+20 suddenly spun faster, as if something had violently rearranged its interior. Then in 2004, another magnet at SGR 1806-20 unleashed a starquake so powerful its gamma ray flash temporarily blinded satellites and ionized Earth's upper atmosphere. From 50,000 light-years away, if that quake had happened within 10 light-years of us, the radiation could have triggered a mass extinction, proving that even dead stars can reach across the cosmos to threaten worlds. Here's where it gets even stranger. These quakes don't just shake the star, they rewrite its magnetic field. A neutron star's magnetic lines are like rubber bands stretched to the breaking point. When the crust shifts, those lines snap and recoil, whipping charged particles to near light speed. The result, a lethal pulse of X-rays and gamma rays shooting into space. Some scientists think these magnetic snap crackles might explain fast radio bursts, those mysterious deep space signals we still don't fully understand. But the most mind-bending consequence is how these quakes ripple spacetime itself. The abrupt crust movement sends gravitational waves pulsing through the universe, distortions in reality so subtle we've only recently learned to detect them. Future observatories might use starquake waves to map neutron star interiors like cosmic ultrasound, revealing what matter becomes under pressures so extreme atoms cease to exist. So while these ultra-dense stellar remnants may seem inert from afar, they're actually seething with pent-up violence. Every crack in their diamond-hard surfaces, every magnetic rearrangement, is a reminder that the universe's most extreme objects are anything but peaceful. Their cosmic pressure cookers and starquakes are their way of letting off steam, with enough force to bend the fabric of reality itself. Galaxies aren't just drifting through space, they're racing towards something we can't see. Across the cosmos, entire clusters of galaxies are streaming in the same direction at speeds exceeding 1,000 kilometers per second, as if pulled by a cosmic current we can't detect. Astronomers call this phenomenon dark flow, and it's one of the universe's most unsettling mysteries. These aren't random motions, they're coordinated, like leaves caught in a river flowing toward an unseen waterfall. The strangest part, this motion defies everything we know about cosmic expansion. According to the Big Bang model, matter should be scattering evenly in all directions as space itself stretches. Yet something enormous appears to be tugging galaxies off course. The scale of this anomaly is staggering. Studies of over 1,000 galaxy clusters reveal they're all being dragged toward a single patch of sky between the constellations Centaurus and Vela. Whatever's pulling them must lie beyond the observable universe, a structure so massive its gravity bends the fabric of reality across billions of light years. We're talking about something that could dwarf the Great Attractor, the previously known gravitational anomaly that pulls our local group of galaxies. This new mystery force suggests there's far more to the cosmos than what's visible from our tiny corner. The leading theory, a gargantuan concentration of mass, perhaps a supercluster of galaxies or even exotic dark matter, lying just beyond our cosmological horizon. Picture a mountain so vast its shadow falls across valleys too distant to see. Other explanations are even more radical. Some physicists speculate this flow could be evidence of a neighboring universe exerting gravitational pull through higher dimensions, like magnetism leaking through a wall. If true, it would be our first glimpse of the multiverse, not through telescopes or particle detectors, but by watching how entire galaxies move against the cosmic tide. Yet skepticism persists. Dark flow challenges fundamental assumptions about the universe's uniformity. The cosmic microwave background, the afterglow of the Big Bang, shouldn't show irregularities on such vast scales. When scientists first detected this motion in 2008, many dismissed it as measurement error, but subsequent studies, including analyses by NASA's Wilkinson Microwave Anisotropy Probe, confirmed the anomaly. The data reveals galaxy clusters moving in unison like schools of fish, their velocities impossible to explain with known physics. What makes dark flow so unsettling isn't just its existence, it's what it implies about our place in the cosmos. We may be part of a structure so enormous it reshapes the motion of galaxies across unimaginable distances. And if the pulling force lies beyond our observable universe, we may never know its true nature. It's like being adrift at sea, feeling the tug of a current whose source lies beyond the horizon, knowing something immense is out there, hidden by the curvature of space-time itself. For now, dark flow remains an open question, a cosmic clue scribbled in the motion of galaxies. As new telescopes probe deeper into space, we may yet decipher this gravitational whisper from the universe's unseen depths. Until then, it stands as a humbling reminder: the cosmos is far stranger and far more interconnected than we ever imagined. The universe won't last forever, but how it ends remains one of cosmology's greatest debates. Two terrifying possibilities loom over our cosmic future: the Big Crunch, where everything collapses back into a singularity, and heat death, a slow fade into eternal darkness. These aren't just abstract theories, they're radically different visions of existence's final moments, each with its own brutal physics. Picture the Big Crunch first, a reverse of the Big Bang so violent it would make black holes look gentle. If the universe's expansion ever slows enough for gravity to take over, galaxies would begin falling back toward each other, accelerating as space itself contracts. First, galaxy clusters would merge in catastrophic collisions, their stars torn apart by tidal forces. Then, as temperatures soar, cosmic background radiation would grow hot enough to boil planets alive. In the final hours, atoms themselves would disintegrate as protons decay, until everything, every star, every black hole, even space-time, is crushed into a dimensionless point. It's cosmic déjà vu, a return to the infinite density where it all began. Now contrast that with heat death, an ending so bleak it makes the Big Crunch seem merciful. Here, expansion never stops. Galaxies drift apart until their light can no longer reach each other across the growing void. Stars exhaust their fuel over trillions of years, leaving behind cold husks of degenerate matter. Black holes evaporate via Hawking radiation, their final moments flashing like dying light bulbs in an infinite cavern. Eventually, even protons decay, reducing all matter to a thin gruel of subatomic particles separated by distances so vast that no new interactions occur. The universe doesn't explode or collapse, it simply runs down like a neglected clock, reaching absolute zero with a whimper that echoes through nothingness forever. The deciding factor, dark energy. If this mysterious force weakens over time, gravity could still win, triggering the Big Crunch. But current evidence suggests dark energy is holding steady, or even strengthening, making heat death the more likely scenario. There's a haunting irony here, the same force accelerating cosmic expansion, which lets galaxies and life form in the first place, ultimately dooms the universe to icy solitude. Yet both scenarios share a chilling commonality: time's end. In a Big Crunch, time itself would cease as the singularity reforms. During heat death, time loses all meaning when change becomes impossible. Our universe's fate hinges on forces we're only beginning to understand, reminding us that existence's grand story, whether it concludes in fire or ice, is still being written. Some planets don't just die, they're melted into oblivion by their own suns in a slow-motion apocalypse. Take Kepler 70b, a real-world hellscape orbiting so close to its dying star that its surface temperature hovers at 7,000 degrees Celsius hotter than some stars. This isn't just a scorched world, it's a planet being actively vaporized, its rocky surface blasted into a comet-like tail of ionized gas as its host star swells into a red giant. The tragedy unfolds with brutal inevitability. Billions of years ago, Kepler 70b might have resembled Earth, a stable world in the habitable zone. But as its star exhausted its hydrogen fuel, it began expanding, its outer layers engulfing inner planets while bathing Kepler 70b in intense radiation. Now the planet orbits its star every 5 hours, so close that its atmosphere has been stripped away, leaving behind a molten core glowing white-hot under constant stellar bombardment. The gravitational forces at play are equally extreme, with tidal locking ensuring one side of the planet permanently faces the star, creating a day side hot enough to vaporize titanium and a night side where any lingering gases might briefly condense before being blown into space by stellar winds. This isn't an isolated horror story. Astronomers have spotted multiple planets suffering similar fates like WASP-12b, a gas giant so close to its star that it's being stretched into an egg shape, its atmosphere bleeding into space at 60 billion tons per second. The star's gravity doesn't just heat the planet, it actively devours it, pulling material away in a spiraling stream of superheated plasma. Hubble observations captured this grisly feast in ultraviolet light, revealing a smeared-out wake of planetary debris stretching hundreds of thousands of miles into space. What makes these exoplanet apocalypses so chilling isn't just the violence, it's the inevitability. Every star like our Sun will eventually become a red giant, and when ours does, Mercury, Venus, and likely Earth will share Kepler 70b's fate. The process might take millennia, but the outcome is certain. Oceans boiled into space, continents melted into lava oceans, and the very atoms of our planet scattered into the stellar wind. Even gas giants aren't safe. Stars in their death throes can ignite erratic fusion bursts, blasting planets with pulses of heat so intense they flash into plasma. Yet these doomed worlds offer scientists a macabre gift, a preview of our solar system's distant future. By studying how different planets respond to stellar death throes, we learn how atmospheres evaporate, cores collapse, and orbits decay. Kepler 70b's nightmare might one day help humanity predict, or even survive Earth's ultimate expiration date. For now, these exoplanets stand as cosmic tombstones, reminding us that in the universe, even death isn't peaceful. It's a spectacle of fire and fury played out across the galaxy. Somewhere in the cosmic dark, an invisible leviathan is dragging our entire galactic neighborhood toward oblivion at 14 million miles per hour. This is the Great Attractor, a gravitational anomaly so powerful it bends the paths of hundreds of thousands of galaxies like leaves caught in a cosmic river. Found lurking behind the dense stars of the Milky Way's southern hemisphere, in what astronomers call the zone of avoidance, this enigmatic force has puzzled scientists since its discovery in the 1970s. The scale of its influence is staggering. Everything within 250 million light-years, including our own local group of galaxies, is being hauled toward it against the backdrop of universal expansion, as if space itself were a conveyor belt tilted toward some unfathomable destination. What makes the Great Attractor so unsettling isn't just its power, it's our inability to see it. Normally, such immense gravitational pull would come from an equally immense concentration of mass, like a supercluster of galaxies. But when astronomers pointed radio and X-ray telescopes toward this region, expecting to find a celestial metropolis, they uncovered something far stranger. The Norma Cluster, a modest gathering of galaxies, accounts for only a fraction of the observed pull, the rest of the mass nowhere to be seen. It's as if we're being dragged toward a ghost, a cosmic illusion where the math insists something monstrous must exist, but our eyes find only void. Recent observations suggest this mystery runs deeper still. Behind the Great Attractor lies an even larger structure, the Shapley supercluster, 860 million light-years away, containing more than 20 massive galaxy clusters. Some theorize this gargantuan assembly might be amplifying the Great Attractor's pull like a gravitational megaphone. Others propose dark matter, the invisible scaffolding of the universe, has clumped here in unprecedented densities, creating a shadow metropolis we can't directly observe. The most radical hypothesis, the anomaly might be a remnant of the early universe's asymmetry, a primordial kink in space-time left over from the Big Bang that never smoothed out. Yet for all its mystery, the Great Attractor isn't an existential threat. It's more like a cosmic landmark. Our local group won't reach it for tens of billions of years, long after the Milky Way has merged with Andromeda and new stars have stopped forming. By then, dark energy's accelerating expansion might have stretched space so thin that even this gravitational behemoth's pull will be overcome. But its existence forces us to confront humbling truths, that most of the universe's mass remains invisible to us, that galaxies move in currents we're only beginning to map, and that even as we peer deeper into space, the cosmos keeps its greatest secrets just beyond our sight. So while the Great Attractor tugs at our curiosity as relentlessly as it tugs at galaxies, it's also a reminder. The universe has always hidden its most profound mysteries in plain view, waiting for us to look closer, think deeper, and question everything we think we know. From hypernovas capable of sterilizing planets to rogue black holes wandering unseen through the cosmos, the universe operates on a scale of violence that defies human comprehension. We've witnessed galaxies torn apart by collisions, stars vaporized by quasars, and even space-time itself potentially unraveling in a silent instant of vacuum decay. These aren't abstract threats, they're active processes shaping the universe around us, proving that creation and destruction are two sides of the same cosmic coin. Yet here we are, a fragile species on a pale blue dot, surrounded by forces that could erase us without notice. The very atoms in our bodies were forged in these cataclysms: gold from neutron star mergers, oxygen from supernovas, uranium from kilonovas. We're made of stardust, yes, but also of stellar wreckage, the debris of violence on a scale we can scarcely imagine. That's the paradox of our existence. The same events that could annihilate us also made life possible. A nearby gamma-ray burst might strip away our atmosphere, yet without the heavy elements blasted across space by such explosions, Earth itself would never have formed. So which of these cosmic horrors unsettled you the most? Was it the thought of a primordial black hole drifting unseen through our solar system, or the chilling inevitability of the Big Rip tearing apart atoms themselves? Maybe it was the realization that our sun, the source of all life, could one day swell into a red giant and reduce Earth to a molten cinder. Whatever keeps you gazing at the night sky with equal parts wonder and dread, share your thoughts below. This isn't just theoretical doom-scrolling, it's a reminder that understanding the universe's violent nature helps us appreciate the improbable oasis we call home. And if you think we've explored every cosmic nightmare, think again. The universe is full of unsolved mysteries, from the true nature of dark matter to the possibility of other dimensions lurking just beyond our perception. Hit subscribe so you don't miss our next deep dive into the cosmos' darkest corners, because in a universe this vast and violent, the next revelation might be even more mind-bending than the last. For now, take solace in this: while the universe is indifferent to our existence, we're uniquely equipped to witness its grandeur and unravel its secrets. That's no small feat in a cosmos where even the emptiest stretches of space hum with the echoes of ancient cataclysms. The universe may be violent, but it's also breathtaking, and we get to be here for a fleeting moment to bear witness to